My understanding is that we have a bar, and the bar is on like a horizontal surface. So it's just resting on that surface. Is that right? And so we are looking top down on what's happening. And the bar does not have a fixed point of rotation. So it's not attached to the table in any way, and the table is frictionless. So if I got all the pieces of the puzzle there together, does that make sense? Yeah.
I thought when end was fixed.
I thought that was part number 9, one end is fixed.
Oh, yeah. Okay. Sorry.
I'm just making sure because I want to make sure I get the details right. I don't have the problems up in front of me. So the piece of clay is going to strike the bar and stick to it. And then the system is going to progress. First, without having a fixed pivot point, the system will pivot about its center of mass. So that's something to tuck away in the back of your mind. Without having a fixed pivot point, there's nothing to apply an external force to the system, which means that momentum will be conserved and angular momentum will be conserved. So in this case, I have to consider both. The way I see this problem is the following. I see a case like this, the moment before there's contact, with this object having some velocity v, mass m. And I believe the bar is it just capital M?
On 11, the mass of the bullet is 1 m, and the bar is m.
All right, so I'm just going to make that 2m, so it's the same problem. Now, let me make sure I'm doing the right question, because I don't remember the word bullet being in this at all. All right, yeah, that works. I'll leave it like that. So I'm going to treat it like that. And yeah, the bullet, if the blob of clay is half the mass, is it okay if I use 2m and m like this instead of 1/2? All right, so again, you have to find a way to get a handle on what's happening. So here's how I've decided to get a handle on what's happening. There's going to be the instant after the collision. And the instant after the collision, the clay and the bar are going to have both a velocity like this, and there's likely to be some rotational velocity as well. Everybody agree with that? All right. I don't see any other conditions happening. This isn't hung in such a way that there's going to be gravity acting on the system. So I think I just need to work the problem out from here. Part of it's going to be easy in that I think I can begin by looking at just the momentum of the system. Since the clay sticks to the rod, the momentum of the system before the collision is merely going to be mv. The clay sticking to the rod means that after the collision, the two things combine and have one mutual velocity. So this is going to be the velocity of the center of mass after the collision, which appears to be 1/3 of the original velocity. Any question about that part? Yeah.
Okay, so no matter how far away the blob is from the center of mass, the linear velocity is always going to be the same.
Say that one more time. No matter how far away from the center of the block strikes, then I didn't hear what you said after that.
So no matter how far away from the center of mass, the mass hits the bar, the linear velocity after the collision will be the same.
Well, there's no other external force on the system. So from that vantage point, there'd be nothing to accelerate it any differently. So yes. But I'm trying to choose my words carefully, because there are issues with where it strikes the rod, and we're about to see them. Our next job is to consider angular momentum. That would be the next thing for us to do. And again, I would accelerate this problem so that we're considering just the moment right before the collision. So the ball is like right there. So I can use the perpendicular distance to calculate angular momentum. And to count angular momentum, just a quick refresher, that's going to be R perpendicular mv. After the collision, the piece of clay is going to stick to the rod. So after the collision, I'm thinking we're going to have I omega, and these should be equal. This is conservation of angular momentum. But here's the problem. Where do I measure this from? If X has been measured from the middle of the rod, say, and that's what X was given at before, or if X was given from the top of the rod, doesn't matter. I just need to pick a point of reference. Then I could solve this problem by just putting X in there for the perpendicular distance. The problem is that this has to represent the distance from the pivot point to where the piece of clay touches. Where is it going to pivot? It's not going to pivot about the middle. It's going to pivot about the center of mass. And I don't know where that is. In order to do this problem, the thing that you're going to have to come to grips with is that you need to figure out where the center of mass of the system is. If the center of the system, or the center of the rod, is at its middle, it's a uniform rod, so that's the center of the rod. When the clay attaches to the rod, the center of mass is going to shift towards where the piece of clay is. And this will be R perpendicular. I need to figure out where that is, because that's also going to be the pivot point. So when I want to calculate my moment of inertia, I have to calculate my moment of inertia about this pivot point. So it sounds like for me to progress in this problem, I am going to need to find the center of mass of the future system, the system that exists when the clay is attached to the rod. Now, I have choices to make here, and they're not all great choices. I need to figure out where I want to make my measurements relative to. Like, where do I want to measure the center of mass? Do I want to measure the center of mass from the end of the rod? I could do that, but that's probably a poor choice. And I say that because if I make this measurement, then I'm going to get this distance. And I don't want that distance. I want the distance from the pivot point to where this thing touches. And I'd like it probably based on something that has the length of the rod in it. So I think we should choose the center of the rod as our place to make our measurements from. We get to choose this position. Remember, we are choosing where to make our center of mass measurement from. I can choose any place along the rod or any place in space that I want. So this choice of where to kind of find this distance is up to me. So I think I'm going to choose the center of the rod as my point of reference. That way, when I calculate X center of mass, I have two contributions to this. So let's consider maybe a different picture for the time being, something that will help us. We have figured out where the center of mass is. So it's 1/3 of the way between where the center of the bar is and where the piece of clay is. I don't know if we need that piece of information. What we really need is this distance. This is the distance from the center of mass of the system to where the clay strikes the bar. And from the last part, that was 2/3 X. So right here, 2/3 X. Excellent. And remember, x is the distance from the center of the bar to where the actual clay was. That's what we're using as our reference. I know this is a lot. Ready to keep going? All right. Seems like I'm pretty close to done. All I need now is the moment of inertia of the system. However, the pivot point of the system is the center of mass. Ah, yes, this problem. I love it. So here we go. 1/6 ml squared plus 2/3 mx squared, all times omega equals 2/3 xmv. There it is. I have two answers. The center of mass of the system travels at 1/3 v. The rotational rate of my system is given when I solve that for omega, which I'm not going to bother to do. Could cancel out all the m's. There's one in every term, but that's it. So I get an x in the numerator and an x squared in the denominator. It's a mess. And you could probably reduce the fractions by multiplying 6 across top and bottom. That'll get rid of all the fractions, but I'll let you guys do that. That's just algebra. There's probably more to this question, but if you can get to this point, you're kind of get the other part. There's probably something about energy. I don't want to do that because whatever I get here, bless you, I would have to square it for 1/2 I omega squared. And I've decided just right now I don't want to do that. I could if you'd like. I just don't think it's that interesting to keep going here. I think we've kind of done enough work. Level of difficulty is pretty maxed here. Pretty maxed. Other homework question? I mean, I'm willing to explain more of this if you want, but I think we hit the high points. I was trying to, this is a hard question, very hard. What I wanted you to see here are 3 things, and I don't know if you saw them. I wanted you to see that with the object not fixed in place, momentum is conserved. So linear momentum of the center of mass of the system is conserved. Angular momentum is conserved. But in a problem like this, you have to find out where the center of mass of the system is going to be in order to do the problem. The actual execution of the problem, well, it's a mess, alphabet soup all over the place. But the hard part about this problem, the really hard part, is that you have to figure out where the center of mass of the system is going to be after the collision, and then work backwards from there to figure out everything else ahead of time. That's tough. And of course, shifting that center of mass really, really screwed up the moment of inertia. It made for a very complicated moment of inertia. So just make sure the clay hits the center. Then there's no rotation at all, right? Do you see why that's true? Because if the clay hits the center, x would be 0. And there would be no angular momentum before the collision, so there'd be no angular momentum after the collision. And the center of mass of the system would stay the center. So aim better, and you have no problem. Yes, sir?
Can you find the moment of inertia about the center and then do the parallel axis theorem? Like have the blob or whatever it is, count that as moment of inertia and then do the parallel axis theorem? Does that work?
Could I find the moment of inertia of the system about the center and then use parallel axis theorem to shift it?
Yes.
I think the math is the same, so yeah. You're just adding them in the opposite order. No other homework questions? It's good for me then. All right, so here's my rod. This distance is just x. And that's going to represent the distance from the center of the rod to where the piece of clay hits the rod. Generally, I think we can assume that x is going to be less than L over 2. Right? If x was greater than L over 2, then it's over here someplace and it misses the rod altogether and there's no problem. So everybody understand what I'm saying x is? And this is also the center of mass of the rod. Okay, so I want to find out where the center of mass of the system is. And I think it's like right there, but I don't really know where it is. I want to find it. So to find it, I'm going to use the center of mass formula. I think the actual one in your book is M times R, but same idea. Good luck. So let's start with the fact that there are two masses here. There's the mass of the rod, and since we're using this as our reference point, the distance from here to the center of the rod is 0. Agreed? So I can say that that's going to be the mass of the rod, 2m, times 0. Then I have the piece of clay. The piece of clay is striking the rod a distance x away from the center of the rod. And it just has mass m. The whole thing has mass 3m. Any question about that? So this is where the center of mass of the system is. And x center of mass, let's see, will be 1/3 of x. So that tells me that this distance is 1/3 x. And that tells me that this distance is 2/3 x. You okay now? All right, we're going to come back to this picture in just a minute, but I think we're okay for this. All right, let's go back to our. All right, so back to work here. As I look at this problem, we now have to switch back to figure out the moment of inertia of the system. So let's slide that over to the side and recognize that I see this as having two moments of inertia. The moment of inertia of the rod plus the moment of inertia of the clay. And it all has to be relative to the center of mass of the system. That's this place right here. So this part's not so bad. The clay is a point mass, right? It has no shape, so I don't have to worry about it. I can just treat it as a point mass. So the clay's moment of inertia will be m, and the r in this case is going to be the distance from the clay to the center of mass. That's 2/3 x. Quantity squared, of course. But the rod is not spinning about its middle. The rod is spinning about a new axis. So I will have to use the parallel axis theorem to take the 1/12 ml squared for the rod's middle and add to it a shift. Oh, wait, I've already made a mistake. The mass of the rod is 2m. And let's shift it, 2m, and I have to shift it by 1/3 of x. Now we're talking. Put all that together, and the moment of inertia of our system will be 1/6 ml squared plus, see, 1/3 squared is 1/9, so 2/9 mx squared plus 2/3 squared is 4/9, so plus 4/9 mx squared. 4/9 and 2/9 is 6/9, and 6/9 is 2/3, right? Just like an overview real quick. As I go over these questions, the thing that I think you should pay attention to is not the answers. I mean, the answers are important, true, but you guys understand that most of your credit in all of your AP questions comes from the process. So although I did not write all the questions in your homework, This one I did right. So those numbers and everything are all garbage. I say that's based on this. It's fake. It's the point of the problem is to wrap your head around what's happening in this instance. And I would say that of all 12 questions, this is the one that's probably the most far afield of your actual test tomorrow. Does that make sense? Meaning it's probably the most far away from what your test questions are going to be like. I'm going to give you an FRQ here in a bit so you guys can see what it looks like on AP to have a problem like this. But I think those of you who have talked to me a little bit understand that what the real difference is that AP is they're going to artificially break up the problem into steps for you. And they're going to guide you a little bit more than what I've done in guiding you on these problems, where I just said, give me this answer. They're going to say, well, why don't you tell me this first and then tell me this? Does that make sense? They're going to give you some places to start and things to think about. So you should expect that. This particular problem, I had several goals in mind, and I'll tell you what those goals are. And the problems that I've assigned, they're not haphazard. They all have something I'm trying to get you to speak to or to think about. And this one was no different. So as I see it, there was a ring portion of the problem. And I'm just drawing this to kind of give us a sense of what I saw when I think of this question. Bless you. Who was that? That was you? You have range. All right, so this is what I think of when I think of this question. So the space station has a central hub. There's something like spokes that connects that central hub to the outer ring, and our space station is spinning in space and creating a sense of artificial gravity for the occupants. Bless you. You can just let it all out. It's okay. Clearly, it's possible. There has been a lot of pollen in the air. I don't know, making fun of sneezes is just something that I think is necessary because sneezes tend to evolve throughout high school. And I think whatever sneeze you leave with in high school is probably how it's going to be for the rest of your life. And I've been teaching a long time. There are people who are scared to sneeze in public. And so they've learned to kind of hold it in. And what you get is this weird combination of sneezes when people sneeze. This time of year especially, it's wonderful. I like the good solid sneeze. Let it out. Move some mucus around. That's what the sneeze is for. That's why you feel the tickle. When the sneeze happens, just let it take you. Like make a whole body experience. That's kind of my belief. I hate the dainty sneeze. So if one of you guys is a dainty sneezer, can't stand that. It's really, you will be deserving of ridicule. So, especially if a hand's involved. Don't like it. I had a student years ago who used to meow after every sneeze. It was always the same. It was a meow every single time. I thought she was faking, but nope. It just happened. It was pretty funny. Luckily for us, she sneezed every day. So we had lots of opportunities to hear it. I had a kid one year who they sneezed every day at the same time, 3 sneezes. They were in my first period class. And within 15 minutes of the bell ringing, just like that, and it was done. And she goes, yes, every day. I go, is it like this in other rooms? She goes, it's every day. Like on a Saturday when you're not here. That's the condition. You should get that looked at. Something with your wiring seems broken. But so, good for us. I recorded all that. YouTube, here we go. So the first thing, luckily nobody watches my YouTube channel, so it doesn't matter. So it's terrible. You did?
It was a little bit difficult to follow at times.
Was it?
Yeah. Especially like when people ask questions, like obviously you can hear them talking, but
Yeah.
So you didn't know what you were talking about.
Sometimes I try to say the question again, but I've been a little complacent this year. Okay, so all of you who are watching at home, you could have just fast forwarded the last 5 minutes. The first question asks you to figure out how fast the space station has to spin in order for the people to experience gravity. Now, they're not going to experience gravity. They're going to experience a normal force. There is no gravity. So they'll be experiencing an unbalanced force. That's to keep them going in a circle. It's going to simulate gravity. We want this unbalanced force to act towards the center. It's a normal force. And we want this normal force to be equal to the weight of the people, so they experience weight. How do you do that? Well, you make that unbalanced force equal to MAC. And you say that the unbalanced force is a normal force, but you want it to be equal to their simulated weight on the planet. Which means that we want the centripetal acceleration to be equal to g. That's all it is. So in this case, because we got an angular velocity, I'd set that equal to omega squared times r. And this will give you how fast the space station has to be spun in order for the people on the inside of the edge of the space station to experience g. To make the problem easy, just use 10. It's supposed to be about the experience, not so much anything else. So I said the radius was 50. So we're out. You'll get the angular speed of the space station. It's 0.2, square root of 0.2 is what, 0.4 something? So 0.44? That would be in radians per second. Now, somebody do me a favor real quick, because I don't actually know this answer and I'd like to. What is 50 times 0.44? It's got to be like around 22. That's how fast a point on the edge of the space station is moving. So this point right here, say, has a linear speed of 22 meters per second. That would probably make people sick, thinking. It's a 50-meter long radius, so we're talking about half a football field's worth. But that edge is going about 45, 50 miles an hour in that circle. I think your body would not like this at all. But it's just a vicious problem. I need to know because of what's going to happen next. The next part of the problem, they say that the people inside the spaceship are all going to go on a run. And they're going to run at 5 meters per second. And they're going to pick a direction and run with the station or against the space station. There's several problems with this particular question that if you're not really invested, you'll miss. So I'm going to make this work because we don't need it. And for just a moment, I want to kind of zoom in on the space station. If the space station is actually spinning as we say it is, people inside the spaceship deciding to go on this run are going to affect how fast they're in the circle. So if all decide to run in the direction the space station is already going, then they're going to be traveling in a faster circle around the space station. It will take more force to keep them traveling in the circle. They're going to be heavier or appear heavier because they're now running faster than the station is spinning. Their angular speed around this circle is greater. So everybody understands? If they run the other direction, the opposite happens. If they run the other direction, they're now running in a slower circle. They're still going around a circle, but at a slower rate than the space station's going. They will appear lighter. If they could run at 22 meters per second, they could be going fast enough so that when they run backwards, they're not moving relative to space. space station would be spinning at 22. They would be backwards at 22. So they would not experience any centripetal force. They'd float. If you could run fast enough backwards, you would be floating. It would be kind of a fun game if you think about it. Run backwards really fast so that you could float, and then the air pressure would start pushing you in a circle, so you'd slowly sink back to the ground. As things to do on a space station when you're bored thing, I'd do that. Now, unfortunately, running 22 meters per second is probably not likely. So I think we're safe to say that these people are always going to be running in such a way that they have a force to allow them to run against the floor. But it's fun to think about. Here's the problem. And you might have difficulty with this problem. Conceptualizing what I'm about to say. They run 5 meters per second. Is that 5 meters per second relative to space or relative to the space station? Yeah? It's got to be relative to the space station, right? For a number of reasons. One, they have no way of knowing how fast they're running relative to space. There's no points of reference. So they only know their speed relative to the space station. Does that make sense? The problem is that when they run with the direction of the space station, they increase the angular momentum of their portion of the system. So the space station has to slow down so that the angular momentum of the system stays the same. If they run against the direction of the space station, then they reduce their portion of the angular momentum of the system, and the space station will have to speed up to compensate. It happens at the point where their tiny little feet touch the sides. If they want to push themselves this way, then they push the space station that way, speeding up the space station. Of course, the reverse of that is also true. If they try to push themselves this way, they push the space station that way, slowing down the space station. They are a relatively small mass compared to the space station. But the problem here is we don't know what the final speed of the space station will be. In fact, that's what the problem is. So let's consider that as what we need to do. We need to figure out what the final speed of the space station is going to be due to them running in the space station. So the first thing I want to realize is this is a conservation of angular momentum question. So to do that, I realize that we're going to have a rigid body, and this is before everybody starts running, and there'll be a rigid body after, but I think that there's two things after. There's the space station and the people, because they are now at different speeds. Everybody follow? Now, before isn't so terrible. I think you're going to need the moment of inertia of the space station, which is actually two parts, the center and the ring. So we could say the center cylinder plus the ring. Plus, you've got 20 point masses for the people. Right? I would treat them as a point mass because they're just little blobs on the inside of the space station. So I think a point mass works for them. There are 20 of them, each weighs 60 kilograms, and they are 50 meters from the edge. They don't have an inconsequential moment of inertia. And this is all times omega, which we have already found. Is that good? Afterwards, there will be the space station and its final angular momentum. We don't know what that speed's going to be. That's what we're looking for. The people, on the other hand, are all going to run in the same direction, lucky for us, although they should do it the other way, right? Everybody runs in pairs and runs in opposite directions so that this doesn't happen to the space station. But we'll do it this way. We don't know what their actual speed is, but we know that they will be running either with the space station or against the space station at their velocity divided by the radius to give us the angular speed of them relative to the space station. The v there is going to be 5 and r is going to be 50. Now, that part's not terrible. But we have to understand this makes their speed relative to the space station's speed. So this is when they're running in the direction of the space station. This is when they're running against the direction of the space station. I'm not too concerned with the numbers. I'm concerned that this is how you lay out the problem. I did conservation of momentum. I was careful to separate out the space station after this because it has a different angular speed than the people do. And I had to make sure that the people's angular speed was relative to the space station's speed, which is why I have that plus or minus 5 over 50. I think we're kind of done with the problem portion here. Yeah.
Since there's 20 people, would you fire and multiply
Oh, yeah, this should be 20.
Okay.
In the other class when I did it, I lumped the 20 in with the I, and so I forgot about that. Now, we could put the numbers in, but I think that that's something you guys can do. This is a cylinder, so 1/2 mr squared, use the 10 meters there. This is a ring, so it's mr squared, use the 50 meters there. These guys are point masses, so mr squared. That's it. The number part does not interest me. It's just a lot of you guys punching calculator buttons and all of you getting different answers and us not agreeing as to why until we figure out who made the mistakes. That's no fun for any of us, is it? But I think you guys can do this problem if you had the numbers. So can we stop here? All right. Is there anything else on the homework you'd like me to talk about? Yes, sir. Excuse me? All right. So question number 6 and question number 11 are largely the same. I don't get much from this about the condition of the rod, except that it doesn't look like it has a fixed point. So I'm assuming that it's fired towards the rod in a condition where there's no friction or gravity acting on the rod. Is that kind of what I'm reading here? You're the first person to ask about question number 6. So if I assume that that's true, there's the rod, and it's just sitting on some frictionless surface. And then there's this piece of clay that's going to strike the rod somewhere. And the piece of clay sticks to the rod. There's something else here I need to make sure I read. All right, so X is this distance from the middle of the rod. All right. Since there's no external force acting on the system, right, there's no fixed pivot point. Because there's no fixed pivot point, and this isn't hung, there's no gravity, linear momentum is conserved. And angular momentum is also conserved. Linear momentum just requires a reference frame. So we can talk about linear momentum right now without having to do anything about angular momentum. In this collision, I believe we're going to have let me just do that real quick. We'll have this condition where the clay is going to be stuck to the rod here. And the rod is going to be moving now with a velocity in this direction, the center of mass of the rod. So with that knowledge, I think we can say that mv for the piece of clay has to equal m plus 3m for the clay plus the rod. This will be the final velocity. And it looks to me like the final velocity is 1/4 the initial velocity of the clay. This is not affected by where the clay strikes the rod. I never had to use anything about where the clay struck the rod for this. This will be the velocity of the center of mass. The problem comes in with me being very careful about the use of the words I'm using here. This will be the velocity of the center of mass. The center of mass of the system is not at the center of the rod. The center of mass of the system is somewhere between the center of the rod and the mass. Meaning, when I look at this, and just give me a moment because I want to do something here. That's not really what I meant to do, but that's where we are. I want to line these up a little bit. The middle of the rod is here. Something like that. That's the middle of the rod. But the center of mass of the rod is probably going to be, center of mass of the system is probably going to be here, somewhere in the middle. Now, the reason why this is important is our system is going to rotate about the center of mass of the system. So in trying to calculate the rotational speed of the system, I have to have an idea of where the center of mass of the system is going to be ahead of time. And that's because the angular momentum of the clay is based on this distance, the distance of the center of mass of the system to where the clay strikes the rod. Is everybody following that so far? So I need to find out where the future center of mass of the system is going to be. So that means this distance is 1/4 x. And this distance is 3/4 x. Now I think I have something from which to work. R perpendicular times mv is the angular momentum of the clay. It's important to understand that R perpendicular has to be measured from the center of mass of the system to where the clay strikes the rod. So that's going to have to be 3/4 x. And that's got to be the angular momentum of the system before the collision. This has to equal I omega for the system. The problem is that I don't know what the moment of inertia of the system is. I know it's a rod, and I know I can treat the clay like a point mass, but it's not a rod rotating about its center. It's a rod rotating about its center of mass. I will need to find the moment of inertia of this system. This has to equal m times, that was 1/4 L squared, right? Plus 3/4 x squared. That all equals 3/4 x mv. All times that omega. There we go. Fun. I think we're just one step away from the answer, and I'm probably not going to do it. I would probably get rid of all the 4's and get rid of all the m's. So that we get 3xv equals L squared plus 3x squared times omega. And then you can solve that for omega. So not interesting, I guess, at this point. But omega is going to be equal to this whole weird fraction, 3x over L squared plus 3x squared times v. And there's nothing you can do about it. That's just the way it looks. Comes out to be in radians per second. That's nice. Says, ask questions about maximizing stuff. Good luck with that. I would say if you shoot it towards the center, there's no spin at all because x will be 0. But x can't be greater than L over 2, right? Or you miss the rod entirely. So I think if you want maximum rotation, you probably fire it towards the end of the rod. But that increases the moment of inertia of the system, so I'm not sure if that works perfectly or not. Now, you guys have had calculus. You know how to find maximums and minimums. Best way for this one is to do, I'd probably say something about the derivative with respect to x. So probably a dw dx would tell you how to get the maximum spin. You guys know how to do all that fancy calculus stuff. So take the derivative, set it equal to 0, find out where it is. But I don't think you should worry about that. If you can make it to here, wow, you've done a lot of physics. It's a hard question. And question number 11 is exactly the same. They are the same question. So just a different ratio of the masses. All right. And let's consider that if I look at just the system for just a moment, without all the distraction of what's happening, there's going to be a time when the clay is going to stick to the rod. Good so far? The rod has a mass of 3m, and the center of the rod is where its mass is for purposes of looking at center of mass. And the rod, I'm sorry, the clay has mass m and is located distance x away from the center. What I'd like to find is the center of mass of the system. I'm looking for this distance called x center of mass. That's what I need. So let's find it. X center of mass is equal to the sum of m times r divided by the sum of m. I have to pick a point of reference, and I think the best point of reference is the center of the rod. Since everything else is being measured relative to the center of the rod, that seems like an appropriate place for us. So m times r for the rod is going to be 3m times 0. R represents the distance from my point of reference to where this mass is in the center of mass formula. The clay strikes the rod a distance x away from the center of the rod, and it has mass m. So the clay's contribution to the center of mass is m times x. And this is all divided by the total mass of the system, which is 3m plus m. This looks to me to be 1/4 x. That means this distance here is 1/4 of x. Here's not a bad idea. No longer dealing with this. And I can keep that there if I'd like. I have this as my pivot point now. So let's start with parallel axis theorem. This is going to give me the moment of inertia of the rod about my new pivot point. Starting with the center, 1/12 ml squared. I'm using L for the size of the rod. I hope that's the right letter to use. What? Yeah, it's 3m. You're right. Plus I need to shift it to where the new center of mass is, 3m, and my distance I'm shifting is 1/4 x squared. That's just the rod. I now need to add the moment of inertia of the clay, which is a point mass. So the moment of inertia of the clay, a point mass, m, in this case, its distance away from the pivot point is 3/4 x squared. So this is 1/4 L squared plus 3/12 is 1/4. Well, there's an m, so I'll put the m out front. X squared plus m times 9/16 x squared. And this is not 1/4. This is 3/16. There. So this is going to be m times 1/4 L squared plus 9, 10, 11, 12, 12/16. Take out the 4 is 3/4. Should probably check my math on that. But I think that's right for the moment of inertia. Nothing we can do about it. That's just the way it looks. So, fun times. you would have to find the center of mass if after a collision, now there's a lot that has to be kind of happen for this to be true. So let's say that we don't have a fixed point of rotation. Just have this thing floating out in space. And I'm using a bar and a disk, but understand it's any two things that could stick together. Okay? So I'm using a bar and a disk because we know things about bars and disks and we can work from there. But it could be a potato and, I don't know, something that crashes into potatoes. Pick something. I don't care. It could be that two thing. And either way, the same circumstance exists. So this thing may be, let's try and keep all the colors the same from before. This thing crashes into the edge of this so that they stick together, become one object. Well, if there's no fixed pivot point, instantaneously after this collision, they will pivot about the center of mass of the system. Also, the motion of the system will track the center of mass. So depending on what's happening, this system will rotate. And it's going to rotate, about this center of mass position. So if we're trying to get an idea of that, I'm not sure I can get an idea of that. Let's see. Do something like that, rotating about its center of mass as it travels around there. I don't really have the ability to animate this well, but you would need to know where that center of mass is if you wanted to know what this angular velocity is going to be after the collision. Yeah. If there's no fixed axis, if there's nothing holding it in place, there's no reason to believe that the center of mass wouldn't move due to the collision. Does that answer your question? Yes, I believe the center is going to move. Conservation of momentum only exists if there's an external force on the object. Only exists if there's no external force on the object. In the case of an object that is free to move, there is no external force acting on the object. So during this collision, whatever amount of linear momentum this object had, the system will now have to have that linear momentum. And that will have to be the momentum of the center of mass of the system. Yes, sir.
So if we're in the situation where it's rotating about its center of mass and like the disk will let go or detach while it's spinning, would the bar then rotate about the new center of mass or would it continue rotating about the old center of mass?
It would instantaneously change to rotate about its new center of mass. Probably after wobbling a little bit. Because it would have to restate where the new center is. And it has angular momentum about a certain point now. So once you separate, it will transition. I'm not sure it would be instantaneous, is what I'm trying to say. All right. So, I answered that question. Yes, Allison.
My question just kind of goes to in question number 2 and number 3, why we didn't calculate the change of center of mass when we did use energy to find the angle. That was such a question to answer.
As I said in class about those two, we have a slightly different condition there. And I believe it was this class where we showed it. But I don't want to, I'm not trying to suggest you weren't paying attention. That's not true. The bullet was really small compared to the 2x4. Although it contained a lot of momentum, it does not substantially change the center of mass. 2 kilogram 2x4, that is, 4 meters long, and a, 20 gram bullet. I think we found that it shifted the center of mass such a small amount, it was nearly unmeasurable. And so under those circumstances, there was not enough of a change of the center of mass to arguably make much of a difference in the answer. So it's nice when that happens. Is that thorough enough? All right. Anything else? So the problem begins here with a fixed pivot point here at the end. And somehow it's being held sideways, even though gravity is acting on this object. So I assume whoever's holding it holds it until the ball hits it and lets go at the exact moment the ball hits it. So some magical system takes place to make that happen. After the ball strikes it, it becomes a single object that has a combined, combined motion. So something like that, right? It's going to spin now after this. Now, it's going to acquire a certain amount of velocity due to the collision. The ball already got some velocity because it fell this distance. So just before the collision, without me doing any real work, I think we can all say that the ball has a velocity of the square root of 2gh. It fell a distance h, so mgh equals 1/2 mv squared. I don't believe I really need to talk about that state of the problem very much. Are we okay with that? So the ball makes it to here, and now we have a collision where the ball strikes and hits the rod, and the rod and ball now have a combined angular velocity. Okay so far? Now, here's the thing. If the ball and rod have a combined angular velocity, there's also a gravitational force that's acting on the center of mass of the rod. Agreed? It's going to cause the rod and ball to swing around. Everything okay with that? Now, you're asked to find some other stuff, but let's answer the question you asked me. But is there anybody who needs to go through any other part of this problem before I go to answer the question she asked? Which part? I couldn't hear you, so. Okay. So I'm going to treat the ball as a point mass, a distance. What are they using here? I don't know what the numbers are. I don't care. What's the mass of the bar? It's the mass of the ball. And what am I using for the length of the bar? Moment of inertia of the bar plus moment of inertia of the ball. So the bar, I would say, is a uniform rod rotated about an end, 1/3 capital ML squared. Add to it the moment of inertia of the ball as a point mass rotated about a distance L away. There it is. That's the moment of inertia of the system. I don't have to calculate it from a special point. It's rotating about the end. So I can just use the end as my point. I don't have to find the center of mass or anything like that for this portion of the problem because it has a fixed pivot point. Now, if I wanted to find out how fast it was going at the bottom of its arc, then yes, I'd probably have to find either the center of mass of the system or I'd have to find the change in gravitational potential energy of each individual item. Your choice. And then convert that all into kinetic energy of the system. Is that okay? All right. So, anything else before I answer the question I was asked? The question is, how high do I have to lift that ball so that the thing will go all the way around? Well, I don't have to do all the way around. I know if no energy is lost to the system, that this arrangement we have right now, let me just grab this. No, I'll grab that. That's what I want. Let's take that. Just give me a second to figure out how to do this without having to redraw everything. All right, let me take that over here, clean it up a little bit. And there we go. That'll do. That didn't work. This thing's going to go all the way. I probably should put it on the other side. That would might make this better. Mr. Sheldon, you guys should expect better from your teachers. Today's just not going well. Let's just get you out of the way. Get you out of the way. And put you over here. All right, so after the ball strikes it, it's going to come all the way around to here, so that it will have the same angular velocity here as it had when it left. Conservation of energy says that has to be true. So although it will convert the gravitational potential energy it has here to kinetic energy when the whole system is down like that, when it gets down there, that kinetic energy will be converted back into the same amount of potential energy it has when it's perfectly horizontal again. Does that make sense? So, and I don't have to get it to go all the way around. I just need to have enough velocity here for it to make it perfectly vertical, right? Gravity will bring it back around. So I need to know what velocity do I have to have here so that the system will go up and become vertical. That's all I really need to know. If I can figure out what that velocity is, then I can use that to figure out how high the ball has to get above there. And since this velocity comes right from the collision, I think I have a way of relating omega to h. You should already have this relationship from the collision. So should we do that collision portion first? I think that'd be a good idea. That'll give us our relationship between this angular speed and how high the ball is above the rod. So let's do the collision. I might need the moment of inertia later, so let's assume we're going to hold on to that. Everything is just connected, and I don't understand how it's connected clearly. There, just get that all out of my way. And let's bring this back down. There. So the ball has a velocity equal to the square root of 2gh. That is the velocity of the ball just before the collision. Now, this is a collision question where angular momentum will be conserved, the instantaneous moment before the collision and the instantaneous moment after the collision. I have to say it like that because gravity is acting on the system the whole time. So it's actually increasing the velocity of the ball all the time. But for the collision is just the instant before they touch and the instant after they touch. There's going to be a change in the velocity of both. The ball will be slowed down because it hit the bar. The bar will be sped up. And it's going to have something to do with their inertias will determine what the final velocity is. That's why I'm using, momentum for that. The momentum of the ball is based on its point of closest approach, which is going to be this distance L. So the ball's angular momentum is going to be equal to R perpendicular mv. Those are all the pieces for the ball's angular momentum just before the collision. You all good there? Just make sure before I go on, could you assemble that on your own? R perpendicular mv. So, you guys okay treating it as one object after the collision to get omega? If we do, then that's going to equal capital L. This is not the length. This is the symbol for angular momentum. that will equal I omega. And the I in this case is going to be what we already did, 1/3 capital M L squared plus little m L squared. So if I set these two things equal to each other, I get 1/3 capital M L squared plus little m L squared omega equals L m times the square root of 2GH. There's a relationship here between H and omega. Are we okay with that? The question was, how high do I have to release the ball so that when they collide, the system goes all the way around? So now I know the connection between how high I lift the ball and how fast the bar will be going when it makes it part of the way around. What I'd like to know now is how fast does the bar have to be going so that it will continue and go upwards 90 degrees. Are we okay with that? Because you need to understand that before I go on. Because it's moving, right? It went around, it's still moving. If it's not going fast enough, it won't make it all the way up. If it's fast enough, it'll come all the way up and over. Okay? So what I'm going to do now is consider, move all that over there, the fact that this moving bar has to now tip upwards 90 degrees from this pivot point and take the ball with it. There. And I have to make it just to the top. Your choice. Do you want to do this as talking about lifting the center of mass, or do you want to treat these as individual objects? You brought up the question earlier, so I really don't care. All right. Center of mass of the system is going to be lifted from this point, from this height, to wherever that center of mass is. I think the center of mass is going to be somewhere between the midpoint and the weight. Okay? I'm setting here as my new reference level and saying that the bar has only rotational kinetic energy when it's here and has all gravitational potential energy when it's here. That okay? All right, here we go. This is going to be my H. I'm using a lowercase h, not to confuse it with the H for the ball. All right. So 1/2 I omega squared from here is going to equal mgh here. And I'm using just a generic m. This is actually not the mass. This is, I mean, if you want, I can say it's going to be m plus m because we're lifting the center of mass. So now I need to find out where that center of mass is in order to lift it. So I'm going to make this 0 for measuring x center of mass. Boy, Mr. Sheldon, why did you give them this homework question if you don't even like doing it? Because they need to pay their dues. And I think they've gotten complacent with homework. So x center of mass, that's a summation. It's mr for the bar and mr for the disk divided by m plus m. Right? That's how you do center of mass. So for the bar, this will be capital M times L over 2. That's how far away the center of mass of the bar is from 0, times the mass of the bar. The disk, mass little m, is located distance L away from 0. because the disk is up there. The whole thing has a total mass of capital M plus little m. This is distance to the center of mass of the bar. More importantly, this is h. Okay? I have to substitute now, if that's all right with all of you. This should be fun. M plus M times G times H, which is M times L over 2 plus M times L, all divided by M plus M. Gorsh. However, you guys are smart people, probably a little bit stressed now, but pay very close attention to what I'm about to do. Not a big difference, just thought I'd make some parentheses go on. Do you see that that cancels out? Everybody see that okay? If not, that better? When that cancels out, I'm left with G times M times L over 2 plus little m times L. If I distribute this G, I get mg L over 2, the amount of potential energy in the center of mass of the bar, plus mg L, the amount of potential energy in the disk. Right? Does it really matter if we use the center of mass or just treat them as individual objects? Some of you might have found this easier to do. Can't use that for other stuff like, dealing with the momentum and having it rotate about the center of mass, but you could have done that. And for some of you, that might have been easier. This is the bar. This is the disk. You guys see that? I mean, really? I'm hoping. Either way, this has to equal 1/2 I omega squared. But wait, there's more. 1/2, 1/3 ml squared plus ml squared. That's I, right? Times omega squared. Well, somewhere around here we had an omega. I've since lost it. Oh, there she is. She be peeking out right there. I don't really like where this is going, but you asked, so we shall continue. Let's just, for poops and giggles, let's just walk over here and say omega equals LM square root of 2GH over, just a moment of inertia, but boy, probably should have just left it I. It would have been easier. There. I know we can cancel an L, and you might feel like that we should. Don't. Just let it percolate for just a minute. Jumping Jehoshaphat. This is going to be a lot. All right, so let's bring it all together. mg L over 2 plus mg L equals 1/2. Boy, I could just put an I there, and that would make me so much happier. But no, I think you guys should suffer. 1/3 ml squared plus ml squared times LM square root of 2GH divided by 1/3 third, my highs are starting to cross, L squared plus ML squared. Okay. Okay. Now all we have to do is solve that for H. So, Mr. Shelton texted out last night. Does anybody have any questions they want to ask about their homework? I'd be happy to jump online and maybe host a tutoring session. I got one reply. Nope, we're good. So, yeah, I'm sure you guys were great. I know that this is ugly, but I can cancel one of these with one of the ones that's there, so that helps a little bit. So there's really nowhere to go but algebra, and I really don't want to do it, but I don't know, something about this tells me that why not? I'm going to multiply both sides by 2 to get rid of this guy. So that gives me MGL plus 2MGL equals LM root of 2GH over 1/3 ML squared plus ML squared, and that's squared. And I know it's getting down towards the bottom there, so let's hike it back up there. You might not see what I'm about to do, so this is L squared. Do you see that? There's an L squared in both terms in the denominator. There's no way around this, though. I need to get H by itself, so I need to multiply both sides of this fraction by the denominator. Okay, we're almost there. Just because I kind of know where this is going, I'm going to write this a little bit kind of wonky. I'm going to write this as 2mg times m times h on the right side. And then all of this stuff is still on this side, so I'll just put ditto. Now, here's why. I'm going to get h by itself. And I have mgl plus 2mgl all times 1/3 m plus m divided by 2mg divided by m. Just separating them out. These things belong together. They're all mass. They have no units. Kilograms divided by kilograms. This side belongs together. You notice the bottom is just mg, twice the weight of the ball. The top is the amount of energy necessary to get to the top. In fact, factor out the L, and I get mg divided by mg, a unitless quantity. So take that L out, take it all the way out front, and you get a massive fraction necessary to tell you how high the ball has to be. And it's based on some percentage of how long the bar is. You see that, right? You know that part at the end of Mortal Kombat where he's standing there and it says, you know, fatality, and something brutal's on the screen? That's kind of how it feels there right now, doesn't it? But you were the victim and I was the guy playing. Yeah. Yeah. That was a lot. That was so lot. Look at that. Whee! It's a far cry from the little square root of 2gh we did right at the beginning. By the way, that's actually not the answer. Has to be greater than that. Otherwise, the bar just comes up to the top and stops. Oh. All right. In this collision, the bar stops after colliding with the ball. And they're kind enough to have the ball positioned in such a way that the bar strikes the ball right at the bottom of the bar. You understand all the simplifications that are made by that. And the fact that the ball doesn't stick to the bar means none of the center of mass stuff you have to worry about either. And the fact that there's a fixed pivot point, that helps out too. I'm not saying they're all going to be like this. But read question A. Now, it's only worth 1 point. But they are only asking for you to write down what the angular momentum of the bar is. And they give you mass of bar, shape of bar, moment of inertia of bar, and the angular speed. Not asking for a whole lot. That's not a heavy lift there. Question number 2, though, is to derive an expression for the velocity of the ball after the collision. Don't think that's too terrible. 4 points, which means we're up to 5 points. Now, that's not passing the exam. It's a 2. We need to see if we can't eke out 3 more points. Next question is worth 4 of those points. I will say that question C might make you struggle if you don't know what it's telling you. It says, assuming the collision is elastic, calculate the numerical value of the ratio of M1 to M2. The answer is 3. Telling you what the numerical answer is. You might want to write it down. It's 3. But if you don't know where to start, the answer is right here in the wording. If it's an elastic collision, the kinetic energy of the bar will have to equal the kinetic energy of the ball. So if it's a collision that's elastic, you can just set 1/2 I omega squared for the bar equal to 1/2 m v squared for the ball. Give me a minute. Keep in mind, you just solved for V in question 2. Try this one. I will post the solution for this. And I will post whatever work I did on all the classes on the homework as well. And